here joining the audio conference, Dr. Novel. Therefore, your talk presentation is live streaming and recorded. So any audio voices that or any voices that the audience makes will be recorded
During the conference.
during Okay, with that said, I'd like to introduce Dr. Nut. In the few years that she's been with me, she's been one of the most outstanding students I've gotten to mentor and work with me. She received her bachelor's degree in civil engineering in 2009 in Middle East Technical University in Ankara, Turkey, and then coastal engineering in 2011, the same university. And then in 2017, she received her master's in ocean and resources engineering, and now is going for her PhD at 2018 in ocean resources engineering. And one of the most notable things is that she has won a Denise Evans Fellowship in oceanographic research previously, and since she's been with me, she's helped also run the hydraulics lab, coastal engineering resilience lab. So her experience has been really invaluable. Her experience uh, borders everywhere from coastal management, as you were just in the presentation. She's worked with in situ measurements, oceanographic measurements, and then is very familiar with wave-3 and wave modeling. And she has also been a valuable teaching assistant. She's taught a couple of our civil engineering courses. In fluid mechanics fundamentals, she was teaching for myself and another professor. And then also in vulnerability and adaptation coastal infrastructure, where she basically was my right-hand person in helping me lead the class, which is a project-oriented class. And a couple of really notable projects that she's worked on is in modernization of coastal process modeling, and then also has worked in climate adaptation in the North Shore of Oahu area. So, and then she helped me mentor numerous undergraduate students. So anyway, I'd like to introduce and welcome and look forward to your talk after that. Thank you.
The ways that you are watching at the video are recorded in February 2016 edit competition. North Shore's famous is a gift for Hawaii and it shapes Hawaii's key identity, that's true. But as a scientist, as an engineer, when I was watching this, one question that was already in my mind bothered me even more. What would happen if there is a change in the driving mechanism of these swells? How much effect will cause to Hawaii? What you see in slide 3, the driving mechanism for these giant swells are extratropical storms. They create swells that are long distance traveling, coming to our island Hawaii, and affect the Hawaii sea state. So what would happen if there is any change in these extratropical cyclones? And how much swell change it will happen in Hawaiian Islands? And what does it mean for our shorelines, for Hawaiian shorelines? What you see in slide 4 here is that the main mechanism of any kind of a change in extratropical storms are barochronicity. Because it makes sense, barochronicity is a change in warm and cold air masses. So extratropical cyclone formation is basically the potential energy stored in the background circulation in forms of the temperature gradient and vertical wind shear converted into kinetic energy. So if there is any change, it will happen in temperature gradient, will affect the wind shear, and will affect the barochronicity, and will result in intensification in extratropical cyclones. What scientists found that increasing number of surface aerosols or the greenhouse gas concentrations or in the mid-latitude ranges, the latent sea surface temperature gradient increase, or in the polar latitudes, the ozone depletion, and even in the headway south expansion, they all change and impact with the variable temperature gradient. And that is one of the main reasons that we have a change in the biochemical history. And the consensus that is found is that the extratropical storm cyclones and the strong ones are becoming stronger and become more frequent, and they are also moving forward. What you see in slide 5 here is that indeed the extratropical storm in the graph, extratropical storm cyclones, the strong ones, are increasing. What scientists found that they estimate in 100 years the number of strong extratropical cyclones that we are going to see is going to increase about 50%. And when we make measurements through satellite altimeter and wave buoys, we saw that there is also more extreme wave height events are happening. And scientists also associated them with the change in the extratropical cyclone characteristics. So when I was thinking about my research, I realized that there is an uncertainty in linking these extratropical cyclone storms and the swell trends in Hawaii, and how much it will change the Hawaiian shorelines. So therefore, what you see in slide 5 here is my research goals that I divided into 3 parts. The first one is I'm trying to answer what is the relationship between the strong extratropical cyclone and the swell characteristics in the Hawaiian Islands. And the second thing that I'm trying to answer is that how much this trend of the extratropical cyclones from generated swells are changing, and if there's a change. And then lastly, what is the impact of the extratropical generated storm swell on the vulnerability of the Hawaiian shoreline? So the outline of my talk, as you can see in slide 7, is divided into 3 parts. First, we are going to generate the extratropical storms, and we're going to see what the methodologies and the results are. And then we're going to create the waves, and then see what is going to affect in the wave trends. And then we're going to see the impact of the coastal these swells on the coastal shorelines using the coastal vulnerability model. So let's start with the extratropical storms. What you see in slide 8 is that when I was thinking about the extratropical storms, of course, they are wind values. So the wind data set that I used is climate forecast surface reanalysis data set. The reason that I choose this data set because in upper percentile wind ranges, it captures the extreme events better. So it can give me a good number of through more the measurement of the extratropical cyclone events. But in the data sets, in the literature, there are different tracking algorithms are happening. So that causes uncertainty in understanding which tracking algorithms that they may lack in capturing the real events. So there's a lot. Therefore, I choose the extratropical identification algorithm. So basically, if the data set is satisfying my constraints, which are 3 constraints that you are seeing on this board here, then I said that okay, this is my extratropical event is happening, and I'm recording that event. The 3 constraints that I choose, the first one is the mean sea level pressure minimum. This is important, and I set this the data value to 970 hectopascal to just capture the strong extratropical cycles, not every one, just the strong ones. And the second one is the geopotential height at 925 hectopascal level. The reason that I choose this 925 because it is good to give me the pressure gradients, but also low enough and low enough to give me pressure gradients, but high enough not affected by the surface winds over there. What you see in the picture in the slide 8 here is that this is Alaska, northeast, northwest shores of US, and this is a contour map of the geopotential height. What the red or pink dominated area that you see is where the geopotential height is captured minimum. So if that point also satisfies my other 2 constraints, then I store that as an event. And these 2, mean sea level pressure minima and geopotential minima, will help me to capture synoptic events. Extratropical cyclones are low pressure core and synoptic range events. And so these two are helping me to capture the slower moving events. But these events can happen, like let's say that there are some smaller events at the end of the synoptic range, or there are some events that happens very fast and develops very fast and dies very fast. So how are we going to capture those small scale ones too, or fast developing ones, using the relative vortex? The reason that I use 850 hectopascal level because the friction in that atmospheric level is minimal. And also, you may realize that, oh, I mentioned that these events are baroclinic. That's true. They start as baroclinic, but when the front, plated front develops, meaning that it reaches its peak, moment, it turns into barotropic. So it doesn't depend on temperature anymore. So that's why none of my constraints have the temperature in them. And lastly, the duration from 979 to 2018, 38 years, but 6 months starting from October to the beginning of April period. The reason is that during the North Pacific, the strong extratropical cyclone events and all these surf competitions happen during the winter time. And that's the reason that I wanted to capture the winter, and that's why I used 6 month range. When we look at the extratropical storm characteristics in slide 9, what you see in the first graph is that mean sea level pressure, which my constraint is 970, so you can see that I only captured the strong ones. All these little blue dots are representing an extratropical cyclone event. So through the time starting from 1979 till 2017, all these dots, when the moving average is taken in the red line, and seeing that how the trend is, we see that there is a decrease in the mean sea level pressure. Similarly, what you see in the other graph is geopotential height versus the time, again the same time zone. Again, all these blue events are captured, moving average are taken. What you see is that there is also a still decrease. What does it mean? Decrease in the mean sea level pressure and geopotential height shows that there is indeed an intensification going in the extratropical cycle. And what you see in slide 10 is that when we zoom in to the last 10 years, starting from 2007 to 2017, similar trend values are taken. And what you're going to see that these numbers, the decreased amount of numbers, the changes, are higher than what I showed you before. So this raises an eyebrow. So we need to show special attention in the last 10 years. What is going on in the last 10 years? Because it is more intensified. And therefore, the rest of my talk is going to focus on the period from 2007 to 2017 and how it's affecting its development. What you see in the slide 11 is that the region that I chose is the North Pacific region. And the video that I'm going to show you right now, yes. When you see all these results that is representing the extratropical events, they are not the same number. They are not even the same concentration happening everywhere. If you are careful, that you can see that in 2009 to 2010, and we are coming up in a bit in 2015 to 16, there are more events. Coming up? Yes, there are more events. And on the other hand, during the other, like the 2016, there are less events. The reason is that these extratropical storm events are more happening during the El Nino years, strong El Nino years, and whereas less events are happening, more sparse events are happening during the La Nina times. Another thing that you're going to realize, that I'm gonna start this video again, is that during the strong El Nino season, the events are coming to equator. They're coming closer to Hawaii Island. While in La Nina season, they're going to forward. They're moving further away from the Hawaiian Islands. And what you also can realize that below the 40 north or the 36 around, this area doesn't really have much strong extratropical cyclones going on. So the mostly dominated events are happening around the Aleutian Islands, northeast side of the Hawaiian Island. And so above 40 and north. In slide 12, that when we wanted to see where they are changing these events and plot them against the latitude versus the time of all these years, what it shows us that they are indeed moving forward, and in the last 10 years, more than what is recorded in the literature, almost 3 degrees. So in meridional wise, they are also moving 4.6 degrees westward. So almost like 6 degrees change in the northwest direction in these events are happening. In slide 13, you'll see that you mentioned about that the strong extratropical storms are increasing, and that's indeed true. There are almost like 7 more events are happening every year. And when you see the distribution in the graph that you see, which is the average number of events recorded per month distribution, you can see that there's an increase, starting from the October till the January. January having the highest number of events are happening. However, surprisingly, February, even though it has a slight number of decrease in the number of events, has the strongest events are happening during that time. And then the effect of the winter is ending with the March. So if you are in time limited and only just want to focus on the winter events, you can only just take into account December, January, February to grasp a more better understanding of these events too. In slide 14, so when we have all these events, all these weird events that's recorded, we need to transfer them to the wave environment. And what you see in slide 14 is that all the wave events that can happen in deep water. However, I'm only going to be interested in how the cells are generating and how the propagation is happening. So I'm not going to include all these events that you see in slide 14. But this can tell you that the wave physics, wave model physics that you can see in the deep water, that I'm going to transfer them in a numerical modeling. I'm going to validate my results using a wave time capturing model and a buoy measurements. So let's see what I've used as a wave model. In slide 15, that you can see that I use as a wave model is Waywatch tree model, which solves the spectral action density balance equation for wave number, direction, and spectrum. One key important thing about the wave modeling is the source balance terms, because that can describe you how your wave is propagating through time and how the wind energy is dissolving in the wave spectrum. So therefore, choosing the important wave source model are very important here. What you see here that I included nonlinear wave interactions, nonlinear wave-wave interactions, nonlinear swell dissipation, and when it comes to shallow water, bottom friction and breaking water. But mostly my measurements are taking, as you can see in slide 16, in the deep water. So that's why the first 3 are more dominant source terms for my measurements. The reason that I choose the deep water because Hawaiian Islands has changing, steeply changing bathymetry, and I don't want my measurements to be affected by the breaking or any kind of change in the shallow water mechanics. So that's why I choose the deep water. Another thing is that in order to capture the storm model more accurately, I wanted to use a finer resolution so that I can also capture the high swells, but as well as the small generated swells during that time too. So that's why I used the 36 directional bands, which is 10-degree resolution, in angular frequency as like 50 logarithmic frequency, starting from 0.03 Hz. Another thing that, since I'm distinguishing these swells, is that I use spectral partitioning that's similar to what the Waywatch model uses for the buoy measurements as well, so that I can distinguish how these swells are coming and I put them into swell systems, wave system groups. And I mentioned about that I'm doing the trend calculations. What you see in slide 17, that I use 3 different trend calculations. The first one is the non-parametric Mann-Kendall test, which eliminates the randomness, which looks the randomness of these data series by eliminating the gross errors. What it means, whether I have a significant trend or not. If I have it, Mann-Kendall test will tell me. The second one is the parametric test, is seasonalized linear trend applying seasonal filter. So what does it mean? During the 6 months, my events are not showing the same characteristics. It's changing through month to month. Some February it's becoming more dominant. So there's a season going on. So I decide the seasonal indices and take those seasons out using a seasonal filter and obtain a deseasonalized trend. And through that, I apply the least square regression and obtain my trend. And the last one, Thiel-Sand slope. That's also an unbiased slope calculation because it is not affected by any kind of outliers in your data series. So it's a robust calculation that takes the median of all the trends that's obtained in the time series. So these three, that's what I use in my calculations. In slide 18, what you see is the general swell characteristics during the all 10-year period, 6 months, coming from all the extratropical cyclones. The primary direction that you see in the green graphs here, scattered and histogram, is mostly focused around the 315 and 330 degrees northwest. And the direction, the peak period changes that you see in the red graph, that's mostly focused on around the 13 to 18 seconds. The maximum average wave height that we observe generally, what you see in the blue graph, scattered and the histogram, is around 2.2 meters. However, when we did the peak over threshold analysis, above the 3.6 meters, there are more events, like almost 70 events are happening during that time. And that doesn't mean that it also reflects the maximum event. The maximum event captured during that time, actually during the every competition, 7 meters, coming with the 17 seconds coming from the northwest direction. What you see in slide 19 is that monthly change of all the swells coming from the extratropical storms. So one thing that I would like you to notice is that the change on these months are the maximum deseasonalized trend series that you see in these contour maps. The maximum changes are observed around 0.4 to 0.45 meters, mostly is observed. Another thing that you're going to see is that it is getting redder and redder during January and February, reaching the maximum number, about 0.65 meter changes through the last 10 years. And the strongest month is February, as you can see, and it is dying again, and there is not really significant trend found during the November and December months. When we look at the wave peak periods in slide 20 changes, the monthly changes, that's one thing that you're going to notice, that October starts as like high orange, but the rest of the months are blue. So what we see in the peak period changes, trend changes, maximum trend changes, is that how the extratropical storm front is actually moving. So during the October, let's see it again, that they are orange because they are further away from the Hawaiian Islands. And when the winter comes more and more, becoming February is the dark bluest time. That's it's coming closer, the extratropical storm front coming closer to the Hawaiian Islands. So these peak period changes actually show us that how the front is fluctuating through the seasons. In slide 21, what you see is the wave height contour map for the last 10 years. So one thing that you're going to notice is that the northwest facing shores of Niihau and Hawaii are highest values, because that makes sense. Most of the strong swells are coming from that point and show the highest distance. Another thing is very important in this part is that even though we have more stronger trade winds are happening, or even though the La Nina events are weakening the meridional range swells, you see that this graph is red. So the wave height is actually increasing. And then we similarly pull out the same thing for the peak period. Also, we saw the same thing too. So that means that peak period and wave height is increasing. That shows similar trend with the extratropical cyclones. In slide 22, what I wanted to associate is that I mentioned about strong extratropical cyclones with the swells. So when we correlated these events, we see that indeed the wave height has a significant correlation with the extratropical storm characteristics. Another significant factor here is that all the swells coming from all the extratropical cyclones from the North Pacific, 24% of them are coming from strong extratropical cyclones. And when we compare the maximum trends of the overall extratropical cyclones here versus only just 12 trends coming from the strong ones are higher in trend values. And that I'm going to show you the Oahu results right now because we're in Oahu. What you see in the slide 23 is that the change of the location taking for the northwest of Oahu because it's facing the northwest swell weather, and wave height versus time and peak period versus time. The deseasonalized trend is graphed in the blue line, and what you see in those red lines is indeed an increase in the wave height trends and peak period trends. And that value actually for northwest point, when the overall trend changed for the northwest point, same point of the Oahu, when it was like the wave height for the 0.35, it is from the strong swell, it is 0.51, so it is indeed high. And the peak period is also high, and during this time period. So this change that the increase due to for the strong extratropical storm events in the swells are higher. And you see similar results in slide 24, is that because I mentioned that I used three tests, in the parametric test of the deseasonalized trend series and the TSM, you see that the numbers are close to each other. I took these trends for daily measurements of the maximum values that's observed, average values that's observed, and minimum values that's observed. I show here the maximum and average to give you a better idea. So indeed there is an increase and the values are close together. It shows that I have confidence in my results. In slide 25, like I mentioned all these things, but I also did a validation with the buoy measurements. What I saw is that the blue parts, the blue areas that was sheltered through the island, they were not really capturing good, estimations because they're sheltered zones, so there is a more bias around those zones. And the events are less scattered, so that's a good thing. But and in the confidence ranges. But when I compare that, the wave heights in the locations that's Hawaii location, northwest of Oahu, very good correlation coefficient in the wave height. And in the sheltered zones, that the correlation coefficient decreases. So obviously there's going to be a bias. Which is error biases are kind of similar to what Dr. Lee performed in her study for the multimodal case. That shows that how the wave is traveling through the island. But in general, peak period is showed a little bit lower correlation coefficient, and that's the reason that that's a rough partitioning of the swells. I could have chosen an even finer directional resolution than what I chose in 10 degrees before. But overall, especially in the Hawaii and Oahu points, there's a good representation of the wave systems compared to the buoy measurements. So we talked about all these values in extratropical storm cyclones and swells. What you see in slide 26 is that we learned that almost 25% of the all swells coming from the North Pacific are from strong extratropical cyclones. And we saw the peak and peak period trends of the research. We saw the seasonality in the how this extratropical storm front is moving. And we also saw that there is a significant correlation between the extratropical cyclone events and the swell that's generated. What is really more important too, that how extratropical storm generated swells are increasing in number and increasing in the peak period too. So the front is getting stronger and going forward. That's what it means. And when we compare the two trend differences, the overall swell trends that I obtained, and only just looking for the swell trend that's obtained from the maximum ones are higher. So what does it mean for Hawaiian Islands though? In slide 27, you see our islands that has like lots of features. So and I consider this, but what does it mean for Hawaiian Islands in vulnerability terms? Because vulnerability can be considered as a value. It can be considered as a geological value because it's home for flora and fauna. It can be considered as an economic value because it provides social amenities and economic opportunities from those amenities. And it can be considered as a cultural value because it gives you a traditional livelihood opportunities, can relate with your spiritual significance and give you a sense of place. So due to there are very different estimations of how the vulnerability is, it's important for us to define the general exposure of all the Hawaiian Islands first, and then link it to how the swells are affecting those vulnerability zones. The reason that we want to define the exposure, general exposure first, so that when stakeholders have an idea like they and no money that they want to do something, they can take out the information easily. So that we need to close the gap between the policymakers and engineers. So the rest of my talk that I'm going to show you the general exposure first, and then move into how the high swells are affecting this, because we know that the high wave energy environments are intensifying the vulnerability of the Hawaiian Islands. In slide 28, that what you see in the coastal vulnerability model, that I use the specially based coastal vulnerability model, that first that you put the input variables, the input vulnerability metrics that you see here, geomorphology, elevation, natural habitat, sea level rise, wind and wave exposure, surge potential and population, and also including the structures and the roads in that coastal shoreline area. They are converted into resultant exposure metrics. There are two exposure metrics that we are going to mention in a bit. And when we are defining the coastal vulnerability model, that's, sorry. So exposure metrics in the erosion index is defined by all these three. On the other hand, the general coastal exposure index includes all of these variables. What you see in slide 29 is that how the coastal vulnerability index is created. So we have all these category of the input vulnerability metrics. We rank them and then divide them into percentages. So if it is between the 80 to 100%, it's extremely high, very high vulnerability effect that's created. Whereas from 0 to 20%, it is very low vulnerability created. All these input parameters that after they are ranked, it's put into the calculations of the resultant exposure indices. What you see on the slide 29 is that the general exposure index calculation, which includes all these parameters, geometric average of all these parameters. Okay. But we are using our indices in specially based. So therefore, in slide 30, you see our agent that's helping us to do GIS for our GIS maps to be on top of each other and then get the exposure metrics automatically for us, which is called INVEST, Integrated Evaluation of Ecosystem Services and GIS. What this does us, when we put all our layers that's obtained here, that you can see, and then plug them out as the exposure metric. So for every shoreline segment, it is automatically calculated for us. From all these exposure and vulnerability results, what we learned is that in slide 31, that's given that for considering 7 Hawaiian islands, 31% of the old shoreline segments, because of their morphology, they are exposed to sea level rise, wind and wave exposure, and surge potential. Another thing is that geomorphology and wave exposure has the highest influence in the whole general coastal exposure of Hawaiian Islands. And when we look at each Hawaiian island, one vulnerability metric shows higher influence than the other vulnerability metric. For example, in Maui, we saw that sea level rise is more dominant factor. On the other hand, Hawaii's wave exposure. On the other hand, Molokai, any change in the natural habitat is affecting more general coastal exposure. So geomorphology, natural habitat, and sea level rise, they are different, significantly different among all the islands. And what I mean by the natural habitat is that in Hawaiian Islands that we are blessed to have reef formation, that they can act as a buffer for any kind of wave exposure, but that doesn't mean that they will be, defending no matter what. But that's essential. In slide 32, what you see is one of the results from the input vulnerability metrics. We had geomorphology, natural habitat, and all these 6, 7 indices. But then we just look at the wave exposure because that's what we were talking about. What you see here that the northwest facing points of Hawaii and Hawaii are very extremely vulnerable because of northwest clouds are coming from that part. And the northeast sides of the Maui and the Hawaii are vulnerable also because of the trade winds coming that far. And you see that how the diffraction and the refractions are affecting the Molokai, is showing a low exposure. And what our systems are also giving that how the frequency, how many shorelines that each island has in general vulnerability metrics too. And obviously Hawaii is bigger than all the islands, so it's dominance in the regions, but you can see from each indices which island has more moderate or high shorelines from these graphs. In slide 33, what you see is one of our resultant index. So the one is the erosion index that I mentioned before, which is dominated by, which is created by the geomorphology, wave exposure, and also the natural habitat. So through these maps, that you can see which points that you can direct your resources and act on it. And another thing is that we give like probability density functions of these regions too. So engineers and scientists can estimate what kind of exposure metric can be more seen in the future as well. When we compare the results of the erosion index with the coastal defense structures and without the coastal defense structures, what we see that for Oahu, coastal defense structures are affecting the erosion index almost 30%. But this doesn't mean that we have to build coastal defense structures everywhere because it's changing the natural process of these events. But it shows you whether the coastal defense structure is affecting or increasing in that area, approximately as a rough estimate. What you see in the slide 34 is that our another very big resultant index is the coastal exposure, which includes all the exposure metrics in that area. When we have provided again these maps for all the islands, actually we provide almost 70 maps, and then the probability distribution of these maps almost like 24 graphs for that too, which is coming in our next paper. And you can pinpoint like where the more vulnerable areas and act on it. When we look at Oahu, we see that the Oahu northwest North Shore region and Ewa Beach region are very vulnerable. And when we look at it, for Oahu, over the moderate, meaning moderate, high, and extremely high shorelines are consistent of 21% of the Oahu. Another thing is that even Oahu can, as like the mean average, can show you low moderate vulnerability, but that doesn't mean that the most vulnerable shorelines are not reaching to the high vulnerability graph. So in slide 35, what you see is that our coastal vulnerability index has obviously have limitations because we consider that each metric is contributing to the general exposure value the same way. So it weights the same. And also any kind of the change that happens, for example, in wave exposure is not affecting how the sediment transport is happening over there. So it doesn't interact the dynamic interactions. And it doesn't also consider the quality of the habitat. Whether that habitat is in a good condition or not, same as with the coastal defense structures too. So it's a user's ability, for us ability to decide whether we rank them high or low. However, this model gives you a very good picture of what is going on in that shoreline so that you can start and do your calculations on that. How we are using these coastal vulnerability maps is that we are creating in what you see in slide 36 is to understand the vulnerability in high wave energy environments and propose initial adaptation solutions for that environment to close the gap between policymakers and engineers and scientists. So when we decide our climate stressor for this and gather all the data, we go into two branches. One is the GIS, the other one is the assessment branch. In GIS part, What you see is all these like coastal vulnerability maps are used to visualize what is going on in the back processes and how we are going to estimate the vulnerability in that area, more like quantifying the vulnerability. In the other part, the assessment part, we are looking the impact through ecosystem and community. And once we decide the vulnerability through all these and potential impacts, and considering the adaptation capacity of that region, we decide the vulnerability. The rest is for proposing the initial adaptation solution. So you can have a couple adaptation solutions, and then you go under the multi-criteria evaluation, which considers economic, technical, administrative, social, and one more aspect too. And from all these multi-criteria evaluations, you try to choose which ones that you want to consider, and you apply a simple cost-benefit analysis to obtain the most balanced solution. But this doesn't mean that you're immediately putting all your money into that solution. This process just to decrease the amount of work that coastal engineers is doing, and also communicate this with the policymakers so that they can understand which can give you a most balanced solution, so the coastal engineers can spend more time on the coastal design of that solution process. In slide 37, what you see is that all these big maps, 7 island maps, when we zoom into the region, this in this picture that you see in slide 37 is the Pupukea-Waimea area. You can understand each climate stressor here from these circles, which one is affecting more in that region. So you can understand like which climate stressor is more dominant. And you can easily understand from these colored dots that the red dot is more exposed to that, so that coastal zone is more exposed than the other one, so that you can direct your resources. So after we obtain all these general exposure idea of the Hawaiian Islands, what we want to see, how the high wave energy is affecting them, and how the North Pacific swells are affecting them. So therefore, I created 3 different scenarios to consider. One is the climate, the wave climate is a multimodal state, includes swells and wind waves. The other one is only the swells, and the last one is only just considering the wind waves as a wave climate. The rest of the layers are the same to obtain the general coastal exposure. What I find is that in slide 38 that you see, is that we are looking at Oahu right now. 19% of all Oahu is affected by swells, includes north coming, south coming, east coming, west coming, all swells. So when we just look at the extratropical storm generated swells coming from the North Pacific to the northwest, north, and northeast of the Oahu, it's 22%. So when we compare only just wind waves and the swells, they show different distribution to our statistical results. So all the shorelines, so they affect differently. Well, wind waves are affecting in moderate level. High swells are affected in extremely high level, which you can see in the Sunset Beach photo here, that how the high swells are affecting the area. So what I try to explain here, how to solve that, how the uncertainty coming from extratropical swells, extratropical storms, and how it is affecting the swells in that region, and see how it is affecting the vulnerability. I asked 3 questions in the beginning. The first question that I asked is, what's the relationship between strong extratropical storm and swell characteristics in the Hawaiian Islands? What my results found that there is an intensification in the extratropical storms, especially in the last 10 years. And extratropical storms are strong storms are moving almost like 6 degrees to the northwest level. And when we see the results of the general overall swells coming from the North Pacific, we saw that the trend changes through the last 10 years, 0.4 to 0.45 meters. This is very significant because I know I'm not that tall, but this is 1/4 of my height. So this is a big change for the last 10 years. And what we also see that the maximum trends are reaching and more dominant through January and February months. The second question that I asked is like, what is the trend of strong extratropical storm generated swells in the Hawaiian Islands? One of the significant results that we find is that almost 25% of the swells coming through the extratropical storms from North Pacific are from strong extratropical storms. That's 1/4 of it. And another thing is that there is a significant increase in the wave height and wave periods, which explains us how the extratropical storm front is getting stronger here with the wave height and moving northwards. And we also see the seasonality of that, how these extratropical storms are moving and reaching that they are closest to the Hawaii during February. And for Oahu, the maximum trends you can see on the board. What is really important here, that the maximum trends that you obtain from the extratropical storm swells coming from strong fronts are higher than the general overall swell trend. And lastly, my research question was like, what is the impact of these extratropical storm generated swells in the overall vulnerability of Hawaiian Islands? So we see that geomorphology and exposure, wave exposure, dramatically affects the coastal exposure in that area. And we also see that 31% of the all Hawaiian Islands are exposed to sea level rise, wind and wave exposure, and surge potential. Then we see how these swells are affecting Oahu. 90% of the Oahu is affected by the swell exposure. However, when we just look at the extratropical storm coming from North Pacific, we see that the 22% of the north side of the Oahu are strongly influenced by these swells. So the work can be improved by using a better swell attenuation and measuring through the satellite altimeter measurements. However, the first thing that we need to do, that I'm going to do, is that they extend this time zone from 10 years to 38 years and see that how these swell trends are changing throughout all these years and give a more probability and estimate for the future. And when I think about the probability and estimate too, for all the islands around all islands, I'm going to give another paper, is that 50-year return period and 100-year return period of these swell ready, so the coastal engineers can pick up that numbers and use for their designs. And of course, the coastal vulnerability model can be improved by a better logical statement and including more layers in it. And there is no end to it. However, this is a very good start to understand what's going on in that region. Finally, and my slide 43, is that in the beginning of the video, in the beginning of this presentation, I showed you a video of that how those high swells are shaping the identity of Hawaii. Right? And even though as an engineer, surfers are lucky to have this, as engineers and scientists, we have to think that how much this energy or danger is posing to its community, these giant swells that you can see in this picture that's taken in the North Shore area. So the general idea, the general statement of overall achievement of this research was to link the uncertainty in extratropical storm cyclones with the swell trends to the tropical islands and define and vulnerability of that region. And the main achievement of this work is that the strong extratropical cyclone generated swells in wave height and peak period are increasing as winter is coming. Since this is the final defense, I would like to thank a couple of people, starting from my advisor, Dr. Francis. Thank you so much for all your opportunities that you provided me, and my committee members, and all my ORE family, actually. They are all my mentors. And Dr. Lee helped me quite a lot with the wave watch model, and Ian listened to me presentation to practice. Michelle said she was my first student that I mentored for a thesis, finishing thesis, that meant a lot to me in the work. And Dr. Yang, thanks so much for the sea level rise values, and Dr. Fletcher, thanks so much for your impacts too. And all my founding who helped me to live. And thanks so much for coming here and listening to me.
Please get some food too.
I also want to thank everybody who's watching and my camera.
Okay, I have a question. Yes, so we identified the extreme and extratropical. We have three criteria. So you pick the peak of this extratropical and measure with these three criteria, or how did you identify exactly? Yeah, can you give more explanation?
Of course. So we had the graded wind data.
Yeah.
And in that graded wind data, the algorithm that I look for, first chooses grid point. And around its synaptic range, it chooses the minimum first, the constraint is minimum sea level pressure minimum compared to all its circle. The second, minimum sea level pressure minimum needs to be smaller than 970 hectopascal to capture the storm one. Third one, minimum geopotential height is minimum around the same. So they are all local minimum. And fourth one, relative vorticity, that needs to be the maximum around it so that it can show that it's turning. And also relative vorticity needs to be 5/5 CU to show that it's strong captured one. That all these constraints, or five, that I showed three, but there's constraints, five of them. Then it satisfies. It takes the wind value in that area and then store it, the location, wind height at 10, above 10 meters level, and in that whole synaptic range.
Is it possible for one event you can get the two points?
I use another constraint that I forgot to mention. Thank you. That so in this event, that yes, we don't expect the storm events to just station there. They can move. So if they are in 72-hour range, that the close point that it's moving, that it's considered as one event.
Any other questions?
Very nice presentation,
Thank you.
very impressive research. Couple of comments. There was a paper that came out in Nature Climate Change in 2016, which identified aerosols coming from industrialization of mainland China, stretching across the North Pacific, cooling the North Pacific. And so the gradient between the tropics and the North Pacific was increased, basically accelerating the heavy stuff,
Yes.
speeding up the wind, and creating more of a La Nina-like situation, a La Nina type situation. The West Pacific warm pool expanded. A lot of heat came out of the atmosphere and was stored in the West Pacific sea surface. And this is what's become known as the global warming hiatus. Prior to about 2014, the 2000s up to about 2013, 2014. So there are, in your time series, there are some other processes taking place which might be influencing the trend that you see. And so I'm glad to hear that you're going to be looking at a longer time period. There's also the PDO, the Pacific Decadal Oscillation. So you have sampled only a portion of what that duration is. So there might be a bias in there as well. And the relationship between the aerosols, the expansion of the happy cell, and the PDO is not understood.
Exactly, you're right. Dr. Fletcher said that PDO aerosols and understand expansions not understand and make fake bias in the last 10 years. I totally agree. And I did also a correlation between the PDO and the extratropical storms event that I captured during that time. So I kind of see it a little bit, similar trend in the number of event number is increasing with the PDO index. However, there is definitely an uncertainty in defining why the extratropical storms are changing this much. But what the IPCC report said that different researchers find different results, and there needs to be more time that's recorded. But they say that it is likely that the number is not going to decrease and it's going to increase and become more stronger. So that's just the consensus that's reached so far. But obviously, more research and data is needed. Thank you.
Also, there was a master's thesis in the oceanography department last year by Alyssa Augustin, and she looked at I can't remember the name of the index, but it's like a North Pacific oscillation, and examined the generation of winter swell. I think Phil Thompson and Mark Merrifield were on her committee, so you might look into that.
Okay, yeah, definitely.
Yeah, I think there's a lot of information in there that's relevant to what you've done. And Kurt Storlazzi of the U.S. Geological Survey has published projections for different global warming scenarios, and is concluding that there'll be a decrease in the wave environment as we move through this century. But I don't think he's looking at extratropical storms. I think he's more looking at heavy cell generated wind waves.
Yes. Actually, I also saw in the literature that Sasaki in 2014 said that there is a decrease is going to happen, but they included multimodal space, and I only just look for the slots that, but yeah, I have that's true. Yeah, I'm aware of that.
And then lastly, on your coastal vulnerability index, as you know, we have a lot of historical shoreline change data.
Yes.
And I think that the vulnerability of a shoreline is also influenced by its history. So one that has been chronically eroding is going to have a different vulnerability than one that has been historically improving. And that might be something to consider.
That is true. The erosion index is too simple to understand it. And I know Penny Anderson did all these like shoreline changes that gave me those data and stuff too. And that's true. When we're this TBI maps only just give the general scenario right now. The data that we use from all different agencies, we try to include as much wide as possible, but it's only just mostly 10 years data.
Great,
Thank you.
I get general questions first. From the committee. Anyone? Give a general comment.
Oh, I can wait. Well, I did have a general comment. And as an outside member, this has been really a